Okay, so I'm pretty sure it's recording. Can't really see anything, but if someone was to watch this at home after class, you should have this pass out with you. I can't tell if it's doing anything, y'all. It usually says what?
Like if it's recording, it usually says it at the top left.
Okay, yeah, it's like a little cloud. Okay, so I want to do something here. This is horrible. Oh, y'all, I wanted to record in the first class, but with my house almost getting burglarized. This is a permanent marker, Jennifer. Yeah, no, it was stupid. It ended up just being the wind, but like it was a crazy 9 a.m. class because the whole time I'm teaching, I'm waiting for a phone call from either the cops or my alarm company or my friend to tell me otherwise. It's a bad morning. Okay. I also, y'all, this is elementary / intermediate algebra topic right here. The exponent laws, it's either laws of exponents or exponent rules, either or. Just don't break them is the goal. So if you need help with this, there's videos, right? You could text me on Remind, you can email me, do whatever you want, but there's also videos of all of this. So that's why I'm recording it, because these can get intense and I want to make sure that y'all have this to refer to. So to do a review, that very first rule that we're going to look at, this is called a product rule. Product is going to be the answer to a multiplication problem, right? You multiply two things together, the answer is the product. So if you notice here, they use a, and that's raised to the m. So a to the m times a to the n. Those are multiplying, right? So their answer is going to be a product because so the a's can either be like the number 2 or they can be a variable. Usually it's going to be a variable. So those are going to be my examples, are variables. If you notice, because my a's are the same, what this is saying is if you have the same variable, right, the same bases multiplying each other, right here, it told me to keep my a. So keep your variable, and then you add your powers. So say we have, for an example, x cubed times x to the negative 2 power. You would look, this camera, it's like literally the worst camera. You would look and you would see that those are the same variables, right? When you multiply variables, the rule says keep and add. Keep the variable, add the exponents. So keep the variable. If you add these exponents, you get 3 plus negative 2, right? So 3 and a negative 2 signs are different. You would subtract, you get 1. Keep the sign of the larger. It's just x to the first power, but it's just x, right? Like that's your answer. So if this was an x and this was a y, you can't apply this rule because the rule explicitly shows you that your bases are both a's. That literally means they're the same exact thing. I've been hearing weird stuff, y'all. Okay, feels like it's like Monday and already Halloween or something. Okay, so that rule 2, if you notice, we have a to the m. This is saying if you have something raised to a power, right, divided by the same something, so the same base raised to a power. I want to point this out too. You see how it's m and n and m and n? This is just saying that they don't have to be the same. You can do x squared times x squared. You're going to get x to the 4th, right? Like you don't really think about that because we've done that before. But the m and the n just mean that they don't have to be the exact same exponent, right? The only thing that is the same are the actual variables. It's the base. So then if you look at rule 2, it's saying something raised to a power divided by the same something raised to a power. The rule says to keep and subtract. So what I did for an example, I kind of came out here, y'all, because I did x to the 6th power divided by x squared. If I see something like this, what I'm looking at is, are these the same bases? Are these the same variables? Yes, they're both x. What does the rule say to do when you're dividing variables? It says to keep and subtract. Keep the variable, right? Keep the base, subtract the power. 6 minus 2 is 4. Now, again, y'all, this was x to the 6th divided by y to the 6th. It just stays in that form. Those aren't the same. You can't apply these rules, okay? Okay, so rule 3. Okay, so this just states if you have something raised to the 0 power, it equals 1. So literally, anything raised to the 0 power equals 1. I literally just wrote like x to the 0 equals 1. There are more examples in my videos. You could do 2 raised to the 0 is 1. If you do in parentheses, -2 raised to the 0, that's 1. But if you do -2 raised to the 0, that ends up being a -1. So there's a few little variations that you could definitely see in the video if you watch those. For rule 4, okay, so in parentheses, I have something being raised to a power, and then it's being raised to another power. This would be called a power rule. Oh, yeah, so product rule, quotient rule, right? It's the answer to a division problem is quotient rule. That is the 0 exponent rule. And then this is another power rule. We don't really need to know the names, you just need to know the process. If it looks a certain way, you can apply a certain thing. This would be a power rule. If you look right here, it says a to the mn. So what I did was I kept my base and I multiplied the powers. So what you'll hear me say is power to a power, multiply the powers. It's implied we're keeping the base because it's the only base that there is, right? So an example of that would be like if we have x to the 5th inside of parentheses, and then it is being raised again to the 7th power. Kind of messy because look, it's like right underneath my comma. I was going to do more examples, but there's videos. So many videos. So if I look at this, I notice I have something raised to a power, raised to another power, okay? Power to a power, multiply your powers. X to the 5 times 7. X to the 7 times 5 is 35. Signs are the same, so it's positive. Just x to the 35, that's what you get, okay? Make sure that if it comes up, I'll explain it, but parentheses are really important. One, for entering things into your calculator. If you try to do a fraction in your calculator without parentheses, everything's gonna just be completely wrong, right? Here, if you don't do parentheses, it's a haunted room, y'all. Going down. If you don't use parentheses, it looks like you just wrote x to the 57th power, right? Because the 5 and the 7, they're both exponents, so they're both little. And if they're right next to each other, it looks like 57. So just make sure that you use proper notation everywhere you can. I'm going to come right here. Okay, so inside of parentheses, I'm going to need more room for this one, but I can show y'all on here. Inside of parentheses, I have an A and a B, which says I have different things. Doesn't mean it'll always be two things. It could be x squared y to the 4th z cubed, right? That's just different things. And on the outside of the parentheses, it's being raised to a power. Literally, like burn this into your memory, because what's going on inside of the parentheses is multiplication. You can apply this rule, right? Inside of parentheses, I have a couple of things. It's all being raised to a power. So what you do is you raise each individual thing to the power. Let's do this, for example, parenthesis x, y, close, square it. The a, b, x, y, do you see what I mean? Like they're just different. You could have 4 different terms as long as the only operation going on inside of your parentheses is multiplication. This can become x squared, y squared. Because it's all being multiplied. Now, I don't really have room to write this up like perfectly, so I'm just going to show y'all. This is something that was done numerous times on exam 2, and it's very important that y'all understand that this like breaks laws. If you have, and I condensed it, y'all. Do you see how that's x plus y squared, or it's x minus y squared? Say you have this, because there's an operation in between those terms, you cannot just square the first and square the second, right? Say that was like x plus 3 squared. Wouldn't you expand it, write the parentheses twice, do FOIL, get x squared plus 6x plus 9, right? It becomes a trinomial. So, and that's because of that operation. A lot of people though see this and just go, oh, x squared, that's a 3, so and now it's 9. Like you can't do that. Okay, so make sure that y'all understand that because it's very important. Okay, so rule 6 is, it's another power rule. I just happen to have something in a fraction form, and that whole fraction is being raised to a power. So, and this is just saying I've got different terms, multiple terms. They don't have to be the same. And it shows me right here that my numerator, whatever is in my numerator, gets that power. And whatever is in the denominator also gets that power. So for example, what did I do? I did open x over y and then like cube it. I would have x cubed on the top. I would have y cubed on the bottom. These are all of the rules, so we're going over them sporadically throughout all of chapter 4. We'll see them. I think we see all of them, but I mean, if there's one or two that's not seen, I'm just trying to like include all of the rules because I mean, you just need to know it for math in general, right? Okay, rule 7. Okay, so we have something being raised to a power, right? But my power is in a fractional form. So like here, it was just like x squared, right? Something raised to a power. In rule 7, I've got, say, let me tell you what it does first, then we'll write it. For this one, I've got a to the, and my exponent is a fraction. So what you can do is you can actually write it with a radical using whatever root you need to, where your denominator becomes your root and your numerator is your exponent. I'm going to actually just do it so y'all can see it. I did 4/5. Say we have x to the 4 over 5. And y'all, just so you know, these equal signs in between the left and the right hand side of these, that means if you see it in this form, you can write it in this form. If you see it in this form, you can write it in this form. Like if you do have a problem and it's written with the radical, right? But I'm trying to apply the product rule, like it's gonna be a lot easier to have a fraction as an exponent and then maybe add those together than to try to look at it like this. So these go both ways, okay? That's what the equal sign means. So looking at the rule, my denominator is my root. So this is actually the 5th root of x to the, my numerator is the exponent, x to the 4th. Okay, and then rule 8. So the way I explain this to my intermediate, it actually would be 9. So let's just do rule 8. Rule 8 and rule 9 are very similar. Rule 8 is just showing it to you with the exponent being 1. And then rule 9, since it's an ilm, it's just saying it can be anything, okay? So if you look on the left-hand side of rule 8, I've got something raised to a negative exponent power, right? A correct answer will never have a negative exponent. So what I need to do is actually change that negative to a positive. And the way you do it, this is how I show them. Okay, so a to the negative 1, that's not written in a fractional form, right? So what you do, if it's not written in a fractional form, you write it in a fractional form with your a on the bottom. So this actually became 1 over a to the positive 1. We don't have to write the 1 as an exponent, right? And then if we were to have 1 over a, just kind of flip it, y'all. Say we actually had something written in a fractional form with a negative exponent, okay? Because this is in a fractional form, what I do is I write it not in a fractional form. So now that would be a to the positive 1, right? And what I'll also say too is if it is starting in the bottom, you bring it to the top, right? If it's not in a fraction, it's already up top, you bring it down to the bottom, okay? Doing this is what changes the signs on your exponents. So creepy. Okay, so this is saying something raised to a negative exponent, but like more specifically, not the number 1. What you would do is the exact same thing we just did. It's not in a fractional form, you write it in a fractional form. If it is in a fractional form, you take it out of a fractional form, right? You just go from like the top to the bottom. So say we have like x to the negative 3, and I've already done all these other rules and I'm simplifying this problem and this is what I'm looking at. Well, an answer that's correct would never have a negative exponent. So what I need to do is that in fractional form? No. So what I can do to change the sign on that exponent is actually write it in fractional form. It becomes 1 over x. Now it's cubed instead of a negative cubed. Moving it like this is what changes the sign on your exponent. I didn't do anything for rule 10 because it's kind of self-explanatory. If you have something raised to the first power, it's just something. I mean, I guess we could do like, say you have 2 to the first power. That exponent says how many times you're multiplying it to itself, right? So here I just have 1, 2, There's nothing else multiplying, it's just 2. Y'all, seriously, that's like more words, I think, than each of these different little portions of this lesson. And like I said, there's examples on the videos, and I actually do like more examples per rule. Now what we're going to do is actually start 4.1, which is exponential functions. So an exponential function is written in the form of f of x, like that's your function, right? Like that tells me it's a function. And then the function itself is b to the x. So b has to be a constant. It needs to be positive. It can't equal 1, okay? And that's what we call our base. So I have a b, it's my base, it's a constant, it's positive, which means it's greater than 0, and it's not equal to 1. And then here in this function, our x, that is our exponent, it's also a variable, and it has to be real. Okay, basically just meaning like you can't take the square root of a negative number, right? Because that becomes imaginary. So what I did here was just a few examples of when it is an exponential function and when it's not. I've got a base raised to the x power. So that's greater than 0. It's not equal to 1. It's a constant, right? And then my exponent is an actual variable. It is x, so that qualifies. This second function, 3 base bigger than 0, not 1. And don't get me wrong, these are like whole numbers. Your b can be a fraction, okay? That's actually the difference between these two different functions. But I just don't want you to think it has to be like 1, 2, 3, 4. You know what I mean? It can be like 1/5, 2/7. It can be an actual fraction. In the exponent, I have x plus 1. No matter what I add to this 1, it's not going to make it imaginary, right? It can be a negative number. It can be a decimal. It can be anything that's not imaginary. It can actually be like the square root of something. You could have the square root in your exponent. Okay, that's why I'm saying y'all have to make sure you have your calculators, because those you just really quickly evaluate them and it's done. Okay, unless it tells you to graph it, but I would definitely give y'all some where you just evaluate them. If you look at the not exponential functions, here I have a variable raised to a power, right? A variable raised to an exponent, but my exponent is a constant. It's a number, right? Here I need my x to be a variable. I need it to be something that's not just a number. And so that's why this would fail. Plus my x, that's an unknown, right? This is how we're used to seeing it. But now I need a constant raised to a variable, not a variable raised to a constant, right? For that second one, I'd like no spin math. For that second one, if you look at your b, it's a -1, which is less than 0, which is why it wouldn't qualify for being an exponential function. So now we're gonna actually evaluate these two right here. What I don't like and why I tried to record in my first class, y'all know how y'all can't really see what I do on the calculator? Yeah, when we graph, if you want to go ahead and get your calculator out, you can. The process that I'm going to follow is going to be the same process that I like wrote out all the steps. You remember that one lesson plan? I think it was like 3.5. And I literally wrote like enter variables. Like I did all that. That's the same thing I'm doing here. Y'all just can't see anything. Oh, it almost looked like you could, but probably not. Yeah, no, of course not. Fail. So for problem 1, it says to evaluate using a calculator and to round the approximate answer to 3 decimal places. In your homework, it'll tell you how many decimal places to move it to. And I'm trying to think. That's really it. It'll tell you to evaluate it. It's an approximate answer, so it's not equal, right? It has the little approximation symbol. And literally, y'all, what sucks is you can't see anything, but I will say the words, and it's going to match what you'll see on the help. And if you needed to hear it again, it'll be recorded. So I have a 3. Second mode, I got to go home. I have a 3, that's my base, and it's being raised to the exponent or the power of square root of 5. So same verbiage on your helps, on your homework. It'll say to enter 3, and then it'll tell you to touch the caret button, which is right above your division symbol. It literally is like an upside down V, right? What that does is it moves you up into the exponent area. There's also an X squared button that does the same thing, okay? So 3 caret, second, and then the X squared button, because since my second is blue, what that is doing is selecting the square root, like the radical, you know? And then I enter the number 5, and then I just hit enter. What it gives me that y'all can't see is 11.66475332. Well, it told me to round to 3 decimal places. That's just what you type into your homework, and that's your answer. Okay, so it would be 11.66. I'm rounding here. I've got 47. My 7 tells me to go up, so it's a 5. 11.665 is the approximate answer to evaluating that exponential problem right here. Okay, and then literally, y'all, the next one is 6 to the negative 1.2. Okay, so the exponent is a negative 1.2. That's okay. It's negative and it's a decimal, but at least it's still a real number, right? Like it's not an imaginary number, so you can evaluate it. Y'all, you literally just 6 caret. Okay, don't do the minus, like the subtraction sign. Okay, you have to do the negative right here, negative 1.2, and then hit enter. And you get 0.1164711865. When you round, what you get is 0.11. I'm looking here, so 4 says stay, 6, 0.116. Do you see it's like seconds, right? And you get those solved, you get them answered, you move on in your homework. I would like to put a handful of those on there because, you know, it's evaluating those functions. It's also why I'm saying you have to have a calculator, okay? There's not a way to solve this. We're gonna learn something later. But if you have the ability to solve something in 3 seconds with your calculator, like that'd be more than enough reason to get a calculator and be able to do so. You know what I mean? Okay, so let's switch here to page 2. Okay, so the number E is Euler's number. It looks like Euler, but it is Euler. It's actually one of the most important, fascinating numbers in mathematics. If you go up any higher, you will get to see it and learn a whole bunch about it. And it actually is, it's a very interesting number, okay? And what it is it's a irrational number that is approximately 2.71828182818281828. Do you see what I'm saying? Like it keeps on and keeps on. We write it as E, and there's an actual E button on your calculator. It is with your division symbol, and because it's blue, the way you would type it in is you hit second and then your division symbol, and you'll see you just have like a little bitty baby lowercase e. Okay, if you just hit enter after that, you'll see 2.718281828 because that's actually what it equals, like approximately, right? So instead of entering all those numbers and raising it to powers, that's why we do just E. In the homework, and y'all, we're also going to do 3 decimal places. I just didn't type it. In the homework, there's a few problems where you see your E being raised to a power and it tells you to evaluate. Calculator. Get your calculator, you solve it, you move on, okay? This problem says E to the 2.5, and it's an approximation, right? So you don't have the equal sign there. So second E caret 2.5, enter. I get 12.18249396. So 12.182 and then a 4. So it stays 182. Literally, y'all, that's what you type into your homework and you're done. Okay. Then the next one is E to the 1.9. Right. So we're still following the same things as far as our exponents needing to be real. And even though it's in decimal form, it's still real. Right. So you just do second division to get your E, caret 1.9 equal 6.68589, whatever. Rounding to 3 is 685. I'm looking at 8. So 6.686. Actually could have written on the left, but I didn't, so I had to delete it. Ugliest sight in the world. Okay, hi, can I help you?
I'm just looking at how many seats there are.
Yeah, I don't know. 7, 8, 9, 10, 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 11 times 13, add about 10 more.
Okay, thank you.
You're so welcome. Now we're going to graph exponential functions, okay? All of these little different individual steps are simple, and you just put it all together, and then you're able to graph something. You're not in my class. Okay, so let's graph. First, let me actually kind of define the characteristics of an exponential graph, and then we'll graph, okay? On the left-hand side, I listed the characteristics. For your domain, oh man, y'all have your paper in front of you, right? You can see it's like a really light colored. I didn't know it was that light. That picture, you can kind of see these two little graphs. Okay, I'm not fixing to retrace everything, y'all. The domain of exponential functions is all real numbers. The range of exponential functions is 0 to a positive infinity, because your range is your y values, right? That goes like this. And you notice on your y-axis, you start right here. Like that's where your graph starts. So that's why it's 0. And then it goes up forever. That's why it goes to infinity, right? If your b, so we're talking about an exponential function, right? If your b is greater than 0, what it does is it rises to the right. This is what we call exponential growth. Okay, that's a positive b. I didn't mean to say positive. That's a b bigger than 0, and so it's going to rise to your right. Now, if your b is in between 0 and 1, so this is if it's a fraction, what it does is it actually rises to the left. 1 right here is going to be your exponential growth, and then this one is going to be your exponential decay. So 1 continues to get larger and larger and larger forever and ever and ever, and the other one continues to get closer and closer and closer to 0 because it's continuing to get smaller, right? Like the growth one, they'll say like, you know, the more time you spend at a store, the more money you're going to spend, right? So the longer you browse, the more money you spend. That would be like an exponential function. If you made your x the number of hours you were there, they're saying the higher your x goes, the more money you're going to spend, which makes sense. You know, if you're only there for 10 minutes, you're not going to spend as much money if you were there for 3 hours. Like that's an exponential function. And then like decay, right now I can't think of an actual example, but it would be something that just exponentially continues to get smaller and smaller and smaller. Yeah, something like that. Like I think of science when I think of decay, but I mean, it literally can be anything. It can be money, it could be income, it can be stocks. I mean, it can be everything. So what else was it? Okay, so they don't really go into this that much, but your exponential function is going to be 1 to 1, and it's going to have an inverse. We don't have a mathematical way to find an inverse where we are now, but once we do like 4.2 and stuff, that's when we'll introduce logarithmic functions and natural logs. And like you'll notice, I see that. You'll notice it gets tricky, right? It's y'all, like I'm not kidding, like be here every day, ask questions, watch videos, because it's the easiest thing to mess up. And like you'll be taught that there is an inverse. This is what we're going to use for exponentials, right? So like right now we don't, but we will learn one. An exponential function also has a horizontal asymptote at 0, y equals 0. Okay, that's why the decay continues to get closer and closer to 0, but it'll never equal 0. And that's why whenever you have the growth function, you'll notice that it will be right along that x-axis, which is y being 0. So that's the horizontal asymptote for them. And it's for both of them, whether it's a decay or a growth. So what we're going to do now, I don't understand the lighting. I wonder if I turn, that does not sound like fun. But I wonder if I turn those on, if this would change any. Okay, so what we're going to do now is actually graph, and y'all also can't see this as well, but we're going to graph the function f of x equals 5 to the x power. So after that, we'll write down what the horizontal asymptote is, but hint, I just gave it to y'all, right? And the characteristics, the domain gave it to you, range already gave it to you. The range, okay, so like the asymptote and the domain will remain the same because we're going to apply transformations, right? Now the range is what will change if it has us like flip a function and maybe lift it or move it, or that's whenever like some things would change, okay? But we'll get to that later. If I'm going to graph this, I'm literally going to just pick points. I think in the homework, it gives you the points already. So in an exam, I would give you points also. What I did was I hit y equals, and I input 5 caret x. That gave me 5 to the x, okay? If you wanted to just actually input individually 5, raise it, and do this, see what it gives you, and then input 5, raise it, like you can, okay? This is just the way I do it. Now that it's in my y equals, I'm gonna go back home with second mode. These are the different variables, the different values that I'm inputting for this variable. So that's what I'm gonna do what I taught y'all last time, which is the vars button. So variables, you go over 1, you hit enter again, and then in parentheses, I'm gonna put -2. And then, and I did the negative button, not the minus button, okay? And I'm gonna hit enter, and it tells me 0.04. If you know what that is in a fraction form, that's great. I'd just be careful because it's really easy to mess up. It's actually 1/25. I believe your homework wants it in fractional form, so it would be 1/25. Whenever you graph it, if it's by hand, you could use either, right? After a while, you'll kind of notice that on one side of the graph, it just continues to get closer to 0, so you don't have to be that accurate. I was gonna say something. What was I gonna say? Oh, I get that like right now, it's like really, I mean, y'all, that's an exponent rule. I don't even have to use my calculator. 5 to the -2 exponent rule. That's not in fractional form. I was taught to put it in fractional form. That changes the exponent from a negative to a positive. 1 stays 1, 5 squared is 25. There's my fraction, right? But some of these exponents aren't just x. It could be 2x plus 3. As far as a -2 is concerned, I might not want to do this by hand. And I definitely am not going to want to do all these different x values in my head. Do you see what I'm saying? So that's why I do this. This just happens to be one of the easier examples. So now as far as -1 is concerned, just to show you here, it would be the same thing. 5 to the -1, that's a negative exponent. It's not in fractional form, so I would put it in fractional form. -1 becomes a +1, but you don't have to write 1 as an exponent, right? Because 5 to the first power is just 5. There's your fraction. It's 1/5. Or if it's really ugly, use your calculator. Okay, input it individually each time or put it in that function, and then you can just input the variables as you go along. Y'all, anything raised to the 0 power is what? It's just 1, okay? So because this is just an x and now it's just 5 to the 0, my answer is just 1. And if you notice right here, this graph, this is where it will cross whenever it's in this form right here. That point is 0, 1. That's saying when x is 0, y is 1. This is saying when x is 0, y is 1, okay? So if we do 1, well, y'all, if I do 5 to the first power, it's just 5. If I do 5 squared, that's 5 times 5, which is 25. This example, okay, I get it, not too hard, right? But if it's in a fractional form, like probably would want to use your calculator unless you like actually understand the exponent laws really well and you feel comfortable with those. So just know you have multiple options to figure out your values here, right? So now let's graph it. I noticed that on my y, I go up to 25. So I'm going to do it in 2 space intervals, and I'm going to go up by 5 each time, 5, 10, 15, 20, 25. On my on my x, I noticed that I went to like -2 and 2. So I'm just gonna do like 1, 2, 3, right? And I'm also gonna kind of space that out by 3. It really does not matter. What I'm doing now is no different than what you would have chosen to do. It's just to get this graphed, okay? Now let's actually plot these points. I'm gonna start with 0, 1. So 0, 1, I'm just kind of guessing. I know it doesn't go to that first notch, right? Because that first notch was 5. And then let me scoot over. When x is 1, y is 5. So that's right here. When x is 2, y is 25. So that was right here and right here. Y'all, right here, -1, it's 1/5. Because I see that this one's in this form, I know that this continues to go up and up and up, and this one's what continues to get closer and closer to 0, right? So on an exam, I could very clearly find these points and tell that, yes, you did them correctly. These right here, I would just look on your table. Like, did she actually get the right thing? I don't care if you're not going to sit there for hours, like figuring out where 1/25 is on a little graph. Does that make sense? You just know that these are getting closer and closer to 0. So -1 would be here. And then, I don't know, it's right there. And then -2, I'm getting closer to 0. So now I'm just like pretty much touching it. There's your graph. Like that. Horizontal asymptote, it's an exponential function. It is y equals 0, domain. It's all real numbers, range. That's my y, that's this, right? So on my y, my graph starts at 0 and it goes up forever. So that's 0, infinity. Okay, does that make sense? Yeah. So because of time, I started the last page, which is compound interest, with the last class, but I didn't really get to finish it. So I may finish that on Monday. If we can get to there also today, then that'd be great. So I'm not going to go too much into these transformations. Y'all have seen them. We've done them like a lot on our parent graphs. It's very, very similar. The way it looks is slightly different because now it's an exponential form, and my vertical and horizontal shifts are now called translations. Okay, so if we have a function and it has me apply these transformations to it, I knew that was coming. My vertical translations, so say our function looks like g to the x equals, g of x equals b to the x plus c. So this is a constant being added, right? Like it's away from my variable. So those are the ones that you do what it says, plus c I went up, minus c I went down, right? Does that make sense? Remember, it was like we had a function and like kind of tacked on to the end, I had a constant. Whatever that sign is, you do what that one says. It's the other one that ended up kind of being backwards. So plus c would be up c units, minus c would be down c units. So for the horizontal translations, do you see how my c, my constant, is actually a part of and like right up there in my exponent with that variable? This is going to be when you do the opposite of what that sign is. Since it's a positive constant, you think right, but it's actually left, okay? And then if you have minus a constant, that minus makes you think negative, right? So you think left, but it's actually right. So if it's right there, like touching with your x, you do the opposite. If it's on the outside by itself, you actually like do what makes sense, right? It's the logical answer there. Our reflections, if we have a function and it's an exponential function, and in front of our function, we apply a negative sign, what that does is it causes it to reflect about the x-axis. If our negative is with our variable in the exponent, what happens is it reflects about the y-axis. Okay, so vertical, stretching, and shrinking. If we have an exponential function and in front we have a constant being added to it, it's either going to shrink or stretch, and that's determined by if our c is greater than 1 or in between 0 and 1. So what, 2, 3, 4, 5, like any kind of variation of that, 2.7, whatever. And then like this one between 0 and 1, that would be a fraction, okay? So shrinking would be if our constant's a fraction, stretching would be if it's greater than 1. And then for our horizontal stretching and shrinking, do you see how the constant goes up into the exponent, right? That is going to cause my graph to stretch if it's a fraction, and it's going to cause like horizontally stretch if it's a fraction, and horizontally shrink if it's a whole number. And these are also why I say have your calculator. You can't rely on your calculator. You can't just use your calculator to solve the problems because you don't get the points because you have to actually do the algebra. But if you do know what graph it's coming from, because it usually would tell you, like I'm going to tell you, there's not work here. I'm just going to walk you through it. It told me this was my f of x. it told me to graph this g of x. If you actually put both of these in your calculator, you'll see what it does. You do that enough, you'll kind of just start remembering what these do. And if not, at least you have that as a visual representation to know where you're going, right? So I just kind of wrote out what to do here. In the homework, it'll tell you to use transformations of the function f of x equals 5 of x. It wasn't until I printed them that I realized I used the same one. They must have done the exact same problem in the homework because I just have the homework open and I pull problems. And it says to graph g of x equals -5 of x. So do you see how the transformation that was applied here was that a negative sign was put in front of my function? That tells me that it's going to reflect about the x-axis. So you literally do the graphing tool, and then you'll see a line that does this. So I'm going to grab that line. I'm going to go to 0, 1, because that's where it told me exponential functions cross. I'm going to touch right there. And then the little bottom box asks you if it shrinks by this, I think I should have seen this, right? In the other ones, it'll have little boxes to check for reflections, X or Y axis. So this one, because it's a negative here, and I'm reflecting about the X axis, what I would do is select the box that says X axis. And then you choose the dotted line, and that's your asymptote. You literally just put it right on the x-axis because that's y equals 0. It asks you what the horizontal asymptote equation is, which whenever we found that, we got a y equals. So our answer there is y equals 0. And then this is what I want y'all to see before you leave, because what we'll do is the compound interest, y'all. It's literally plug things in and get an answer. So it's not hard, but we'll do that on Monday. The domain of my exponential functions will be all real numbers. If you're looking at an exponential function that's like this, if you look at your y, that starts at 0 and goes up to infinity, right? If you reflect about the y-axis, the x-axis, when you start right here, it's continuing to go down, right? So it's actually my range is gonna start at negative infinity, and it's gonna stop right here where the function stops, which is at 0. So that's these two different ones, okay? This is the different variations in a reflection. This is what it usually is, and then this is what it will be. That's really it. Okay, I'm gonna do roll, and then y'all can leave. Oh, on Monday, I told y'all, right, is when I'll give you y'all's exams.